Renewable energy is the future of energy, but sources like wind and solar don't often generate energy 24/7. For example, here in Florida, it can either be mostly sunny or mostly raining. If we are to transition completely to renewable energy, we're going to have to address the intermittency challenges. Until then, energy security from renewables is something to think about. In this video, we will discuss how batteries can help us meet our green energy goals, the limitations of our current technologies, and what the ideal grid-scale battery should be in order to support a full transition to renewables. December 12, 2015 is a day marked in history. This is the day the Paris Agreement was adopted by 197 countries, signifying a global effort in acknowledging and combating climate change. With this comes an assessment of our current practices globally that are contributing factors to climate change, particularly how we generate energy. Fossil fuels account for roughly 60% of our global energy production. That's mostly coal and gas, which are one part major contributors in producing carbon emissions. Making a full transition to renewable energy sources is one way we can start to limit our carbon footprint in energy production. But we can't. Not until we figure out a way to make the sun shine every day and generate wind on demand. Energy production from fossil fuels comes from the burning of coal and gas. Coal and gas being a fuel or energy source, which we can produce on demand from mining or drilling oil wells. The extraction of the fuel and the burning of it to produce energy both have significant environmental impacts. But from these sources, we are able to meet our energy needs reliably and constantly. With renewables, the wind and the sun are the fuel, which we can't produce. And whenever energy is generated from these sources, not all of it is usable, unless we have a way of storing the surplus for future or later use, like evenings and mornings, which we do in the form of grid energy storage systems. However, the current technologies being deployed have their limitations. The most commonly used technology is lithium-ion batteries. They are a cost-effective option for many applications, such as cell phones, electric vehicles, and small to medium-scale energy storage installations. Like Tesla's Powerwall, their portable power packs, and even this 250 megawatt system constructed in San Diego, operated by LS Power. But for large-scale full-time grid-scale applications, it's still too expensive since they can only cost-effectively store enough power for 4 to 6 hours. To scale beyond that, the cost will go up significantly and doesn't make sense. Lithium-ion batteries currently cost about $130 per kilowatt hours, and by 2023, costs should come down to around $100 per kilowatt hour. The current average cost of electricity here in the US is $14.91 per kilowatt hour for residential use and even less for both commercial and industrial. There are other technologies such as flow batteries, which use an electrochemical solution to store energy. Thermal storage and other non-chemical options like Energy Vault's gravity storage system, all of which have the potential to be more cost-effective in the future, but still they have major drawbacks when it comes to grid-scale applications. The duration for which these batteries can store and supply energy, their size, and the sustainability of the technology are all things to consider. At the moment, pumped storage hydropower remains the most dominant and flexible system of storing energy. By using surplus energy, which can be generated by wind and solar to pump water from a low reservoir to an elevated one, then released to turn a turbine to generate electricity to meet peak demand or to fill the intermittency gaps. This does require a lot of land and altering of the environment and is simply not applicable in most places. For renewable energy to compete with fossil fuels in reliability, the accompanying battery technology needs to be a long-duration system. The ideal battery should be able to store and supply energy for days instead of hours, and at a price point that is competitive or better than fossil fuels. Iron-air batteries are being revisited as a technology that has the potential to be a long-duration storage solution. An iron-air battery has three simple components: an iron electrode, an air-breathing cathode, and a non-flammable electrolyte solution. In simple terms, it works like this. Air enters into the battery cell and reacts with the iron via the liquid electrolyte. This causes the iron to oxidize or rust. When iron is exposed to oxygen, it releases energy. By reversing the process, that is rusting and unrusting the iron, it can cyclically store and release energy, or charge and discharge. One of the technical challenges associated with traditional iron-air batteries is that they have less than 50% efficiency. Necessity is driving innovations, and Form Energy seems to have figured out how to overcome the technical challenges associated with iron-air batteries. It is yet to be seen since this system will not be ready until 2023. The promise is that this battery will be a long-duration battery, possibly up to 100 hours. It should cost $20 or less per kilowatt hours, and it is sustainable since all the components which are readily available and abundant can be recycled, theoretically. There are other advantages that an iron-air battery has over other battery technologies. Technical challenges aside, these batteries can be more robust and can survive more than 10,000 charge and discharge cycles, and are insensitive to overcharging, partial and deep discharge. This equates to a battery with a very long service life. They are also more energy dense than lithium-ion batteries, theoretically 7 times more. Energy density is not to be confused with power density. Energy density is how much energy a battery can store as per its size, while power density is how much or how fast energy can be delivered. Energy density, represented as watt-hours per kilogram. In this case, Form Energy is promising a battery no bigger than a washing machine for grid-scale applications. These can be strung together to scale for the desired installation, voltage requirements, and duration alike. By the way, if you ever wanted to know the energy density of a battery, here's the formula. Nominal battery voltage times rated battery capacity divided by battery weight equals specific energy, or energy density. Iron-air batteries are not a replacement for lithium-ion batteries, but a long-duration companion to support the decarbonization of our energy grid. The ideal battery technology for a renewable energy grid should not just be one that can deliver on our energy needs, but also one that meets our green energy goals and a true complement to the carbon-neutral infrastructure that it is meant to support. Long duration, cost-effective to scale, configurable, and sustainable. This is how batteries can help us meet our green energy goals. That is it for our video. Thank you for watching.